So we are given a system of 3 distinguishable particles. Okay, so that means we are having n is equal to 3 distinguishable particles, each having spins. So basically we are spin equal to s is equal to 1 by 2. Okay, so we are in fact we are having a system of n 3 distinguishable spin half particles. Okay, so here although they are identical, but they are treated as distinguishable. Okay, such that, and further it's given that Sz this is equal to either plus half or minus half depending upon its alignment along, whether it's aligned along the field direction or opposite to the field direction. So spin either it could align along the field direction or opposite to the field, and corresponding magnetic moment mu z. If we apply field along the z direction, vertical direction, you can say mu z, this is equal to either plus mu or minus mu. Okay, now if we assume that field H, if external field H is applied, okay, then the interaction energy In, interaction energy for spin which align along field okay, if I call that energy as E1, okay, so that means E1 represents the interaction energy of the spin when it is aligning along the field direction. So that interaction energy will be given by minus mu magnetic moment dot H. Okay, so I will call this as equation 1. So this is the case when mu is aligned along H. Similarly, it's also possible that some of the spins may align in a direction opposite to the field direction. So I will call that energy as E2. And when the magnetic moment it aligns opposite to the field direction, the interaction energy become positive, mu H. So that is our equation 2. Okay, when mu align opposite to external field. And if we further assume that H, the field that we are applying, H is along Z direction, which is vertically upward. Okay, so we are considering the vertical upward direction as the Z direction. Okay, and further we will make another assumption. We assume that we will take spin up when we are applied the field along the vertical direction H. So this is the field direction H. So we are further making assumption if the spin is aligned along the field direction, so that is in the upward direction. Okay, so we will take spin up as positive with magnetic moment mu along Z direction, which is mu is equal to mu Z. Okay, and similarly we will take spin down as negative with mu equal to minus mu Z. Okay, so in this way we can arrange the various possibilities, as I'm going to write all possible arrangement of the spin in the table below here. So let's try to understand. So here we will have a state index, okay, and then spin alignment, and third total magnetic moment, and the fourth column we will have total interaction energy. So we need this information, total interaction energy. Okay, so there are different possibilities of the spin alignment. The first one is all the spins they are aligned along the field direction. So that means I am taking all the spins in the vertically upward direction, which is the field direction HZ. Okay, so as I have denoted here, so if all the spins they are pointing in the upward direction, and further we have taken spin up as positive. Okay, so there the total magnetic moment in this case will be 3 mu, because all the spins they are pointing in the upper direction, and the corresponding interaction energy will be how much? For one single spin it's minus mu h. Now we are having a total of 3 spins which are pointing in the upper direction, so the net interaction energy for these 3 spins will be minus 3 mu h. Similarly, the other possibility could be that first 2 spins they are pointing in the upper direction, and third in the lower direction. So in this case here this spin up will cancel with spin down here. Okay, these two will cancel with each other and we are only left with one spin up, so the total magnetic moment for this case will be mu. Okay, and then the net magnetic interaction energy will be minus mu dot h for the second case. Now the third possibility is when first is up, down, and then up. Okay, again the net magnetic moment mu and magnetic interaction energy minus mu h. The fourth case is down, up, net magnetic moment mu. So here one up and one down they will cancel with each other. Okay, so only we will be left with only one spin up, so interaction energy will be minus mu h. Okay, so this way you can work out the different possibilities. Okay, so the fifth one is when one of them is up and two are down. Sixth one will be, now you just rearrange these all arrangements. First is down, up, and then down. And the seventh possibility is down, down, up. Okay, the eighth is that all spins they are pointing in the direction opposite to the applied field. Okay, so now we can write the corresponding the net magnetic moment, and I'm just drawing a line to so that I can write it properly. Okay, the net magnetic moment in this case will be how much? One up and one down they will cancel with each other, so they will cancel with each other. So we are having the one spin left which is pointing in the downward direction, so magnetic moment is minus mu and the interaction energy is mu h. So here also minus mu and magnetic interaction energy mu h. So here its magnetic interaction energy it's becoming positive because we are only left with the one spin which is pointing in a direction opposite to the field. So in that case, so this is the interaction energy for this case. Okay, when spin is pointing in the downward direction, so interaction energy become positive, it's mu h. Okay, so that's why we are having a positive interaction energy here in this case. Here also in case of seventh arrangements, so interaction energy the magnetic moment is minus mu and it's mu h here. And in the third case, all spins they point in the downward direction, so the net magnetic moment will be minus 3 times mu, and here the interaction energy is 3 times mu h. So these are the different arrangements that are feasible with the three spin system when external magnetic field is applied. Now if we take a look at the statement of the problem, so we have to identify the states for which the total energy of the system is mu h. Okay, so here, so only these arrangements 5, 6 and 7 arrangements, they have magnetic interaction energy E, I will call E total, which is subjected to the constraint mentioned in the problem. Et, it is mu h. Okay, so there are only three states. So not 3 states, but 3 arrangements. You can call the microstates also 3 arrangements. Okay, let me introduce another page here. So total accessible microstates which are subjected to the constraint or which satisfies the constraints are total accessible microstates are 3. Okay, which satisfies the constraint. What is the constraint? That E total should be mu h. So we are having, out of 8 total microstates, we are having only 3 microstates which satisfies this constraint. Okay, so and at the same time it's also further mentioned that a state or the arrangement of the spin where the first spin is pointing in the upper direction. Okay, so that is out of these three arrangements, it is the fifth arrangement where the first spin it's pointing in the upper direction, and in the arrangement 6 and 7 the first spin it's pointing in the downward direction. So therefore out of these 3 accessible microstates which satisfies the first constraint of a total energy mu h, so there is only one option where the first spin is pointing in the upper direction. So what is going to be the probability of state 5 out of these 3 states? That's going to be 1 by 3. So that is our first answer. Okay, the probability of having state x. So state x, it's defined in the statement of the problem. It's the one where the first spin is pointing in the upper direction. Therefore the corresponding probability of having state x where first spin points upward in the upper direction, this is equal to, there is only one arrangement of the spin out of 3, so that the probability is 1 by 3. So that is our first answer. Now the next point is, what is the mean magnetic moment along z direction in the state x? The mean magnetic moment along z direction in state x, this is going to be minus mu by 3, because it's 1/3 of the magnetic moment when all the 3 spins they are pointing in the upper direction. So it's 1/3 of that quantity. Okay, so therefore our answer is, let's take a look at the option. So therefore A satisfies this condition, so A is the correct answer here. Let's continue with the next question. This question has been asked in GATE Physics Examination 2021 for 2 marks. The statement is, consider a single one-dimensional harmonic oscillator of angular frequency omega, which is in equilibrium at temperature T. The states of the harmonic oscillator are non-degenerate. Okay, so all the states, the energy states, they are non-degenerate, having energy given by this expression En, that is equal to n plus half h cut omega with equal probability, where n is the quantum number. Now we have to find the expression for the Helmholtz free energy of the oscillator. So let's continue with the energy spectrum of the harmonic oscillator, since it's given that the energy spectrum of a harmonic oscillator given by En equal to n plus half h cut omega, where n can take value from 0, 1, 2, 3 and so on. Okay, let's call this as equation number 1. Now the partition function for the harmonic oscillator is given by Z. This is equal to summation n taking value from 0 to infinity gi exponential, or you can say gn exponential minus beta en here. So since it's given that gn it is 1 here, all the states they are non-degenerate, so we can take it equal to 1. So upon expansion we obtained this is equal to, so before I write expression for the partition function, so let's try to understand the various energy states for the harmonic oscillator. So we will take a few examples, then we will generalize it. Okay, so the ground state energy we obtain for when n is equal to 0 and when n is equal to 1, that's the first excited state of the harmonic oscillator, and n is equal to 2 is the second excited state, and so on. Okay, similarly we can find expression for the higher energy states. So here when we substitute n is equal to 0 in this expression, so that will give us the ground state energy of the harmonic oscillator. So when we put n is equal to 0, the energy become half h cut omega. So that is the ground state energy 1 by 2 h cut omega. When we put n is equal to 1 here, so 1 plus 1 by 2 will be 3 by 2 h cut omega. 3 by 2 h cut omega, and then next will be obtained when we substitute n is equal to 2, so that will give us 5 by 2 h cut omega, and then the next one will be 7 by 2 h cut omega, and so on. So here the first term in the partition function will correspond to this energy, which is h cut omega by 2. So exponential minus beta times e is h cut omega by 2, so beta h cut omega by 2 plus second term, okay, plus exponential minus beta, the energy 3 by 2 h cut omega, 3 by 2 h cut omega, plus next term exponential minus 5 by 2 beta h cut omega, plus so on other higher order terms. Okay, so I will take a common factor outside, so z it becomes, after taking the factor which is common in these terms, so we will take it outside. Okay, so exponential minus beta h cut omega by 2, it's going to be common in all these terms, so I am going to take it outside, exponential minus beta h cut omega divided by 2. Okay, and inside we are left with first term, it's 1 plus exponential minus beta h cut omega plus exponential minus 2 beta h cut omega plus so on. Okay, so this is an expression of type AR square with common ratio of AR. So and we are having terms up to infinity. Okay, so this will be equal to exponential minus beta h cut omega outside, exponential minus beta h cut omega by 2 outside, and then sum of this series, okay, which is equal to a upon a is 1 here, a upon 1 minus r, the common ratio is exponential minus beta h cut omega. So this is the single oscillator partition function. Okay, so let's say this is equation number 2. Okay, now we have to determine the Helmholtz free energy. So Helmholtz free energy, it's linked with the partition function through this relationship. If we denote Helmholtz free energy by F is equal to minus kVt ln z, partition function. Okay, so this becomes minus kVt and then logarithmic of ln exponential minus beta h cut omega by 2 divided by 1 minus exponential minus beta h cut omega. Okay, and this upon expansion gives us, this is equal to minus kVt minus kVt, and then inside the bracket we will have the first term ln E minus beta h cut omega divided by 2, and then minus ln this quantity in the denominator. Okay, 1 minus e power minus beta h cut omega, and then bracket close. Okay, and after, because ln and e they will cancel with each other, so we will be left with, so we will have minus kVt outside, and inside we will have minus beta h cut omega by 2. So beta and kVt they will cancel with each other, and ultimately we will be left here with h cut omega by 2. So I am going to write it directly here. So this is equal to h cut omega by 2, the first term, and then minus that will become plus here, and then minus plus kVt. Okay, so that plus kVt here, kVt ln 1 minus exponential minus beta h cut omega. Okay, and this can be rewritten as h cut omega by 2 plus beta power minus 1 ln 1 minus exponential minus beta h cut omega, where beta is equal to 1 by kVt. So this is our final expression for the Helmholtz free energy, and this matches with the B. It is h cut omega by 2 plus beta power minus 1 ln 1 minus e power beta h exponential minus beta h cut omega. So this is the correct one. We are given a system of two atoms which can be in three quantum states having energy 0, E and 2A. Okay, the system is in equilibrium at temperature T. Match the following statistics with the partition function. So here we are given four different options. So first of all we have to treat the particle as classically distinguishable particle, and then classically indistinguishable particle. Okay, and then by treating them as fermionic particle or bosonic particle. Okay, so let's continue with the first case. So we will for the first case I'm going to the next page here. So the first case that we are going to consider here is, it's the case of the classical and distinguishable particles. Okay, so we are having two particles. We will treat them classically, but they are distinguishable. Okay, so let's try to find out that how many microstates are feasible for the distribution of these two classically distinguishable particles. Okay, so I'm going to draw all the possible microstates here. Just try to understand how we do it. So the energy levels are 0, E and 2E. Okay, and then a few more microstates. We will try to distribute these two particles in different way. Okay, now we are going to distribute, because we are treating the particles as distinguishable particles and we are treating them as classical particles. So there is no constraint in the occupation number here. So that means energy level can have more than one particles also, because they are classical. Okay, so if I label the particles as A and B, so either both of them they could be in the ground state, or the another possibility is here in the first excited state or in the second excited state. Okay, and the next possibility is the first particle is here and the second particle here, and now we can interchange these two particles. The B is here, A is here. In the next option, A here in the ground state and second particle B in the upper excited state. and the next possibility is put A here and B here. Okay, the next one is A here, B here, or A here and then B here. So these are the different 9 feasible, or what we can say is 9 accessible microstates to a system of 2 classically distinguishable particles. Okay, and if I call the total energy E corresponding to each microstates, because both particle here they are in the ground state, so the total energy will be 0 for this system, and here the total energy will be 2E because there are 2 particles in an energy level with energy E, so energy will be 2E. So here we are having 2 particles, so energy will be 4E. Here 0 plus E, here also E, here 0 plus 2E, the energy will be 2E, here 0 plus 2E, again 2E, and here E plus 2E, 3E and 3E again. Okay, now we are having only one microstate with energy 0. Okay, let's see how many microstates are there with energy E. So here we are having 2 microstates with energy E, so that means for this case G is equal to 2, degeneracy. Okay, now how many microstates with energy 2E? So 1, 2 and 3. So okay, I will club these microstates. So there are microstates with G is equal to 3. These microstates have same energy. Okay, 2E. And how many with 3E? So there are only 2. So for this case degeneracy is 2. And how many with the energy 4E? So there is only 1. It's non-degenerate. Okay, now we can write the partition function for this system. So the partition function will be Z classically distinguishable. So I am writing CD here. So this will be sum over all energy states, Gi exponential minus beta EI. Okay, so I will start first of all from the microstates with energy 0. So this will be Gi, this is 1 here, it's non-degenerate. Okay, so 1 multiplied by exponential minus beta e power 0, so that will give you 1. So simply 1 here. Now let's see how many microstates with energy E. We are having 2 microstates, so the degeneracy factor 2 first, and then exponential minus beta E. Okay, now let's take a look at how many microstates with energy 2E. 1, 2, 3. So that is 3. Degeneracy is 3. 3 exponential minus beta 2E. Okay, or I can write it as 2 beta E. Okay, now how many microstates with energy 3E? 2 plus 2 exponential minus 3 beta E minus 3 beta E. So there is only one microstates with energy 4E plus 1 exponential minus 4 beta E. So this is the required partition function when we treat these 2 particles as a classical distinguishable particle. So this partition function matches with, so I am writing here ZCD, this matches with Z3. Okay, now let's take the next case where we treat the particles as classically indistinguishable. Okay, classically indistinguishable, now treating them as indistinguishable. Okay, so in this case, as we have learned in the course of statistical mechanics, so when particles are indistinguishable, so and once the partition function for distinguishable particle is known to us, so then we can connect these 2 partition function as below. If ZCI gives us the partition function when we treat the particle as classically indistinguishable, and then this becomes equal to 1 divided by n factorial, where n is the number of particles, classically indistinguishable particles. Okay, and multiply by Z classically distinguishable. Okay, so this partition function we have already found, so it's here. Okay, and simply because we are having 2 particles, so 1 divided by 2 factorial, that will give a factor of 2, and then Z, the partition function for classically distinguishable particle. So this will gives us the partition function for this case will be for classically Z classically indistinguishable particle, this is equal to, first term is 1, so that will give us 1 by 2, okay, plus the second term was 2 exponential minus beta e. So when we will divide it by 2, it will become exponential minus beta e. Okay, the next term it's 3 by 2 exponential minus 2 beta e, plus next term exponential minus 3 beta e, plus 1 by 2 exponential minus 4 beta e, and therefore the partition function for classically indistinguishable particle, it matches with Z4 in the one of the option. Okay. So now let's take the third case. The third case is when we treat the particles as fermionic, FD particle, FD particles. Okay. So that means when we treat the particles as Fermi particles, so they are subjected to Pauli principle. Okay. So that means we cannot put more than one particle in a single particle state. Okay. So let's see how many microstates are accessible to such a system. Okay. So again we will draw the energy levels. Okay. So we are having only two particles which are fermionic, so energy values are 0e and 2e. So first particle here and second particle here, first here, second here, and the last option is here. So here we cannot put more than one particle. So the energy for this microstate is E, and for this one it is 2e, and for this one it is E plus 2e 3e. So the partition function when we treat the particles as fermionic particles, so ZFT will be, the first term corresponds to this energy, exponential minus beta e, exponential minus beta e plus exponential minus 2 beta e plus exponential minus 2 beta e, plus the third term because of this microstates, exponential minus 3 beta e. So that is the partition function when you treat the particles as fermion. Okay, so this matches with Z1. Okay. Now the fourth case. In this case we will treat the particles as bosonic system. Okay. So now again the boson, either they can stay in as a single particle in any energy state, or all of them they can condense to a single energy states also. So let's see how many microstates are feasible for two boson. Okay. So again we are going to draw the accessible microstates for this system also. So in this case we will have 6 different options. Let's try to understand. So either here the boson, two boson either in individual energy state, okay, like fermion, and the another option, 3 options are they may be in the same energy state. Okay, so the corresponding energies are here E, here 2E, and here 3E, here 0. So here the corresponding energies are 0, E and 2E. Here the energy will be 2E and here it will be 4E. So the corresponding partition function will be Z Bose particle, that is equal to, so first of all the term of the partition function corresponding to E is equal to 0. So that will give us 1, exponential minus beta multiplied by 0, that will give us 1. Then the term corresponding to this energy plus exponential minus beta e, and then the term corresponding to 2e. So we are having only 2 terms here. So plus 2 exponential minus 2 beta e plus the term corresponding to energy 3e, exponential minus 3 beta e, and then the last term plus exponential minus 4 beta e. Okay, so this is the partition function when we treat these as bosonic particle. Okay, so and this is equal to Z2 in the given option. So when we compare all these 4 different distribution of particle in these 4 different cases, so the option C matches with all these results. Okay, so therefore the C is the correct option. So let's take a look at the next statement of the problem. The free energy of a ferromagnet is given by F is equal to F naught plus A naught into T minus Tc M square plus B M4, where F naught, A naught and B, they are positive constant. It's given, and M represents the magnetization of the sample, T is the temperature, and Tc is the Curie temperature. So all these parameters, they are constant. Tc is also a constant here. Okay. So now we have to look for the correct diagram that correctly represents the behavior of variation of M square versus T. Okay. So now, since the free energy for this system is given to us, for the stable system, we have to minimize the free energy with respect to magnetization. Okay. So that means what we are going to do is we are going to minimize the free energy by as a function of m. So this is equal to df by dm. It's a constant, so it will give us 0. Okay. And then from the next term, it's 2a naught T minus Tc multiply by m, and then plus 4b m cube, and this should be equal to 0. Okay. So now we will take some of the terms common. Here in both of these expression m is common, so we will take it outside. So we will be left with 2a naught T minus Tc plus 4b m square multiply by m, and this is equal to 0. Because it's a magnetic system, so this quantity cannot be equal to 0. So the only option that's left with us is that this expression inside this bracket, we have to equate it to be equal to 0. And if we do that, so that means after rearranging the term, so I'm going to write the expression for m square directly. Okay, so we have to equate this quantity here to be equal to 0, and then from here we obtained m square. Let me write it on this side. M square is equal to 2a naught Tc upon 4b minus 2a naught upon 4b multiplied by t, or you can rewrite this as m square. You will cancel some of the common terms from the expression a naught Tc upon 2b minus a naught by 2b into t. Now if you take a look at this expression, and if we plot a graph between m square versus t, okay, all these terms in this expression, they are constant here. Okay, so this is an equation between m square, you can call this as m dash. Okay, so y is equal to mx, where m is this slope which is negative, minus a naught by b. Y is equal to mx plus c, where this c is the intercept, which is equal to a naught Tc upon 2b. Okay, so this relation is best described by option C. Okay, because here it's giving a negative slope between m square and Tc, and the intercept on the y-axis, it is that will give us the information about the critical temperature also. So B is the correct option here. So let's take a look at the statement of the problem. A light source having its intensity peak at the wavelength 289.8 nanometer, which is calibrated as 10,000 Kelvin, which is the temperature of an equivalent black body radiation. Considering the same calibration, the temperature of light source in Kelvin having its intensity peak at the wavelength 579.6 nanometer is how much? Okay, so we have to round off the answer to the nearest integer. Okay, so we can solve this problem by making use of Wien's displacement law. Okay, Wien's displacement law. So what is the final conclusion from this law? So that the lambda, m and t, this will always gives you a constant quantity. Okay, so depending upon the temperature, if the temperature it's changing, so accordingly the wavelength corresponding to maximum peak intensity, it will shift. Okay, so let's try to understand what information is given to us. The lambda 1, this is 289.8 nanometer, and temperature of the source is, let's call this as T1. This is 10,000 Kelvin. This is 10,000 Kelvin. Okay, and we have to find out the corresponding temperature T2, and the lambda 2, it's given, this is 579.6 nanometer. Okay, so then just by making use of this result, we can find out the second temperature. Okay, so that means lambda t is equal to constant. This implies lambda 1 T1, this is equal to lambda 2 T2. So from here we can work out T2, which is equal to lambda 1 divided by lambda 2 multiplied by T1. So then after substituting the corresponding value of these quantities, lambda 1 is 289.8 nanometer divided by 579.6 nanometer, and then multiply by the temperature T1, which is 10,000 Kelvin. Okay, and after solving it, we obtain the T2, it corresponds to 5,000 Kelvin. Okay, so here we can write this is 5,000 Kelvin. So that is our answer.